afterwards. Let me introduce the next speaker, Eitan, Professor Modiano from MIT. He's going to talk about a learning-based influence model to predict cascading failures.
Thank you all very much, and thank you for the invitation to speak at this symposium. So we're going to address a focused and relatively simple problem, that of predicting failure cascades in a power system. So in the power systems, failures tend to cascade, and what may begin as a simple single failure of a power line can rapidly cascade into a widespread blackout. This largely happens because of Kirchhoff's laws. So you might have a power failure. Kirchhoff's laws dictate that if you had a failure on a single power line, that the flow of current on that line has to be diverted to other lines and balanced throughout the network. And as a result of that, other lines in the network may now overload, they may overheat and fail, and this process repeats itself. And while it's rare, it occasionally results in a widespread blackout. And it's important to be able to predict these blackouts so that we can either avert them or respond rapidly. So it's a relatively focused problem that we're trying to address. It's a joint project with my colleague Marie Illich at MIT and Vince Poor at Princeton. All right, so this is the story of the failure cascades. Large-scale blackouts due to cascades happen occasionally. In North America, two very famous incidences include the 2003 blackout. It really started, at roughly 3 p.m. when a power line touched a tree limb in Northeast Ohio. That power line failed. It took a while before anything else happened, but half an hour later, another power line failed, and then 25 minutes later, generators started to trip. And before you know it, suddenly a rapid cascade of events. At 4:05 to 4:07, a whole bunch of generators started to fail. I guess 500 generating units, 10 nuclear facilities, all shut down. The entire United States and Northeast United States, including parts of Canada, was in a relatively long duration blackout at that point. So what we see from that is that there is some time gap. I mean, it wasn't immediate. The cascade took a little bit of time to develop, maybe a half an hour. And then after a certain point, it happened very rapidly. And that's an important point because that's where the benefit of predicting a cascade can be significant. There was a similar event back in the San Diego area in 2011. And the challenges and the features of this kind of a failure cascade are that it's complex, it's highly nonlinear, it obeys these Kirchhoff's laws and so on. But more than that, I'll explain more in a minute. Failures are spatially correlated, but not entirely so. So what might start as a single line tripping in one location, because of the way that the power is redispatched, may result in a subsequent failure far away, not necessarily the adjacent links. And then failures can propagate relatively rapidly. All right, so our goal is to develop a fast, accurate, and general tool that can be used in different power grids to predict failure cascades as a function of initial failure event, of course. So the two main contributions that we hope to obtain through this project, one is a failure cascade predictor. The idea that we should be able to predict the cascade sequence accurately, so starting with a given failure, what will happen over time. And then second, and perhaps even more important, is a critical component identifier that will yield the key components that are most vulnerable to a cascade. What are the power lines? What are the generators that if they were to fail would lead to a large-scale blackout? Why? Because if we knew that, we'd be able to avert such events by taking protection measures. So our approach is to look at failure cascade data from power systems. I'll say much more about that. Sample it, develop what we call an influence model from which we can predict the failure cascade. This is something that we're actually using, both the C3 AI suite as well as Azure's computational capabilities to now develop both the critical component identifier and the cascade predictor. So the methodology is based on our influence model. The influence model is a graphical model that captures the correlation between different components of the power grid. We start with the idea of generating failure cascade samples. I'll say more about that later, but note that this is not easy to obtain such data. It's not as if I can go to the power companies and get sufficient amount of power failure data. Power failures are not that common. But I'll say more about how we do it. We generate failure cascade data. We then have a learning framework based on this influence model. I'll spend some time telling you about our influence model that allows us to predict the failure cascade for a given load profile, okay? Then we feed that into a deep neural net, the result of which is a mechanism to predict the failure cascade for arbitrary load profiles. That's what we really want to be able to have. And finally, we also expand our approach to consider enhancement such as voltage collapse and frequency disturbances and the like. So a bit about our influence model. Our influence model starts with pairwise influences. Just consider the influence of the failure of, say, node 1 on other nodes in the graph. So node 1 may influence the failure of node 5, and we can capture that using a 2x2 matrix that tells you the relationship between node 1 and 5. For example, the first entry of this matrix is the probability that node 5 is on subsequent, if node 1 is on. And here would be the probability that node 5 is off, given that 1 is on, and so on. So that tells you the relationship, the 2x2 relationship between failures of node 1 and node 5, okay? And we can obviously do that not just for 1 and 5, but we can have these 2x2 influences for all pairs of nodes in my network. So for instance, in the same way that node 1 influence node 5, node 3 may also influence node 5, and I can have this 2x2 matrix for every pair of nodes in my graph, in my network. And so now I can use these 2x2 influence matrices to combine all of it and estimate the probability that a given node, say node I, is on at a given point in time. And what it is the weighted sum of those 2x2 influences, where I weigh it over all node pairs. Okay, so I have a weighted sum of the 2x2 influences. So what I've got here is an ability, an equation that lets me predict the probability that node I is on at time t. And the components that fit into this influence model are the dij's, which is the weights for the pairs I and j, as well as the aij's, which is exactly the 2x2 influence model. So we combine all of this, and what we need to do is to learn from the data, both the influences, the pairwise influences, as well as the weights. So we proceed to do that. First, we need to generate data. Generating power grid data, like I said, there is not enough real data out there. We need to have synthetic data. That's the only way to do it. And the way we're going to do synthetic data is literally by simulating the grid. So you take the grid, and you have to simulate the whole complex dynamics here. So given an initial failure, we will implement a load shedding, which is a manual mechanism that happens to rebalance the power in that grid. We calculate the power flows, that one can do. And then you remove the lines that have overloaded again and do the process again and again. That's a simulation, if you would, of what happens in real life. That will give us the sequence of failures in the grid. That will give us the real failure cascade. That will be our input data. You start with a particular line failure, and you see what happens. And we're going to generate a large number of cascading failures like this. That's actually computationally intensive. We are using Microsoft Azure for that with 200 virtual machines. we generate these cascades, and we feed that into learning our influence model. So our influence model, we have to learn two parameters, the A matrix, the 2x2 matrix, that we use Monte Carlo methods for. We literally look at the entire generated data. We look at the subset of nodes that, the subset of instances where node J failed, and then the subset of that where node I failure followed node J failure, and from that we get the entries into our 2x2 influence vector. And then we also have to learn these weights, the DIJs that I spoke about. We solve that using our optimization method, where our goal is to minimize the mean square prediction error, so given by that expression. And this optimization can be done using convex quadratic programming. We can do all of this and get our complete influence model, the result of which is actually a fairly accurate ability to predict the failure cascade. Specifically, in the various experiments we did, what we came up with is 3% accuracy in terms of the final size of the failure. So how many power lines failed within 3% accuracy. For individual power lines, we're able to predict the final state at the end of the cascade within better than 90% accuracy. In terms of failure time, this cascade happens in sequence, in steps. We're able to predict the step we're able to predict that within one step. And all of this is a significant reduction in time complexity, which is the only objective of doing this. We could have always taken this graph and run the whole thing and see what happens. But if we did that, it would take 8 hours to do it. We found that with our methods, we're able to do 1,000 cascades in 33 seconds. So that's the objective of doing that. But that's half the story. And yeah, well, one more thing. The other thing we can do with our influence graph gives explicit relationship between components. And in terms of the AIJs and the DIJs. And from that, we can learn the synthesized influence of, say, the initial failure, say, a node I on some other node J. Okay, and we can sum it up over all nodes to see the total influence from node I to the entire system. That's how much damage it would cause. And from that now, one can obtain which is the most vulnerable node in the graph, which are the 10 most vulnerable nodes in the power system. And that's important because those may be nodes that we choose to fortify in some way, increase their capacities or so on. Just to show you an example of what happens, if I look at the top 10 critical components and generate failures within them, we see large failures with 800 nodes or so. Whereas if I instead sampled from just my training data, the failure size would have been substantially smaller. Okay, but that's half the story. The second half of the story, which will not take me another 15 minutes. The second half of the story is that the load profile varies, especially with renewable energies, okay? So the load profile varies. Everything I've told you so far is I'm given a load profile, tells you exactly the load on every single link. And you can use that, but the load profile is varying. It will be very time-consuming to do what I just did for every possible load profile. To deal with that, we use deep neural net to map load profiles to influence values. We feed enough of that data to be able to have a learning framework that now, given a loading profile, will generate the pairwise influences and the weights that we can feed into our influence model and do all of that in just the 50 seconds that it took me to say. Okay, enhancements of the influence model. My colleague Maria Illich at MIT is also looking into incorporating voltage collapse, reactive power phenomena in the blackout analysis. Another very important enhancement, I think, is to consider that increasingly network systems are interdependent. So, for instance, a power system is dependent on the gas supply system in many, many parts of the world. And an interruption of the gas supply could certainly interrupt your electric power. How is that relationship? Now, that relationship is actually relatively slow, but still worth understanding. An even faster relationship is the fact that increasingly, especially in microgrids, power is needed for operation of telecommunication network. And telecommunication network actually might provide some of the control needed for controlling that microgrid. How is the interdependence there? So for instance, a loss of power can lead to a loss of a communication node, and that can lead to its own kind of failure cascade as well. So those are things we are interested in as extensions. So in summary, we built a failure cascade predictor and a mechanism to identify the critical components in the grid using our influence model, machine learning, and deep learning. We use the computing resources provided to us, thank you, both the C3 AI Suite and the Microsoft Azure. And finally, as we look to the future, extending the influence model to multi-layer networks is one personal interest of mine. Taking into account the more general power phenomena, my colleague Maria Illich is very interested in that. She's working on this. And our colleague Vince Poor is looking at the ability to identify in real time the rapidly changing grid topology as this kind of cascading failure evolves.
Speaker. Are there any questions? Albert.
Alberto Sangiovanni from UC Berkeley. I have just a question. In general, it's very difficult to compute the influence of a node to another node when they are not connected. So I was wondering, how do you
so the process
have these numbers?
Yeah, so I'll tell you exactly. So I did have it there, and I don't know if it's worth going back, but well, I might go back. Maybe not. Let's see. So the process there was here it is. It was this slide. We generate many failure cascade scenarios. For each and every one of them, we generate the entire failure cascade through an emulation of the system. Now we do exactly what I write here. It's a Monte Carlo mechanism, right? I look at all the subsets of cascades where node J failed. I will then look within that all the subsets of node I failure that follows node J's failure. And that will give me an estimate of the probability that node I failed, given that node J failed in the cascade.
So you do simulation, that's what you don't have direct measurements by
Definitely. It's all synthetic data. It's all synthetic data. Call it simulation or emulation, I'm not sure, but it's all synthetic data, yeah.
Costas.
Costas Panos, UC Berkeley. I understand you use synthetic data, but you use it to estimate probabilities. And there is an estimation error related to the number of samples that you have available to do that. Especially since you're nesting so many dependent events. I assume that it will be computationally quite expensive to generate enough data to get enough accuracy to trust the results in the estimated probabilities. Can you comment on the cost of training?
Yeah, yes, I can. It's quite intense. And my students who will be presenting the poster tomorrow have been dealing a lot with that. We have been limited initially to relatively small buses to be able to do this. We're now looking, because it takes so much time to generate enough data, like 100,000 is the number that we're targeting, 100,000 failure cascades in order to train our influence model. Now we're increasing it substantially thanks to the Azure platform, where we're going to be using 200 virtual machines, and even that's going to be challenging, very challenging in terms of how much time it will take us to get enough data. In terms of accuracy, it's a little bit difficult to define accuracy because these are not quite probabilistic events. So it's hard for us to define the probabilistic, the error. However, one can see how effective I am at predicting future cascades.
When I mean about accuracy, I understand that in real life they are not independent probabilistic events, but when you try to estimate these probabilities, This is essentially Poisson distributions that you're drawing from. And the error of those depends on how many samples you have, right? If you wanted to guess whether tossing a coin is 50-50, you have to toss it 1,000 times.
That's clear,
right? So,
yeah.
okay.
That's clear.
Anyway, so my other question related to that is that how do you operationalize this, as you mentioned in the closing remarks, when the real grid is a very dynamic entity which changes all the time? Do you have to redo the training from scratch, or are there any clever techniques?
That's my closing remark. My closing remark was the first half of my talk, which I spent 13 minutes on, required you to train every time. I have a given loading, and this is what I have to do, okay? Then we say, no, I don't want to do that. I'm going to generate many, many of those instances so that I will be able to have an immediate mapping from a loading profile to the failure cascade influence model. Okay, so this is the only reason to do this work, because otherwise you can recompute everything from scratch, and it will take you 8 hours or longer. Don't want to do that. So the reason to do this work is to train a model that will let me predict rapidly in the future for different loading profiles.
Different topologies.
Different topologies, of course. Topology, that's a question I didn't think about that way. So we have not looked at, I assume that the training will be done for a given topology. So you're interested in this particular grid, the training will be done for this particular grid, and I'm going to play with the loading profile. Now, can I also change the topology and learn that? That's an interesting question. I'm not sure.
Hi, this is Swanmesh Bose from University of Illinois. So I had a quick question about your, when you do these Monte Carlo simulations. So do you use a quasi-static model in terms of just power flows, or do you actually simulate the dynamic behavior? Because more often than not, like a power system stabilizer would have some control logic which will trip, which will make the generator stop being connected. And so if you're looking at a quasi-static kind of model where it's just power exceeding a certain amount and a relay tripping, that's a very different ballgame from a dynamic model.
Correct. Definitely in terms of the quasi-static model, when we use DC power flows, we also use math power and AC power flow calculator there too, but I think you would tell me that's also a quasi-static model, right? Because it's not a full-scale simulation. Correct. I mean, one could do full-scale simulation, but then...
Yeah, I have a question, John Burge from University of Chicago. I guess it was whether you're actually modeling the status of the relays, because their failure obviously affects the probability.
So the modeling that we've done so far was looking only at the power lines, not even at this point, but I think it can be extended quite naturally.
All right, let's thank the speaker.
Thank you.
Thank you, Eitan.